So we're trying to see if this is phase known or phase unknown. And at first glance, because we don't have any deceased people, everybody is alive, we might think that this is going to be phase known. However, if we look at an example that we did before, here we said yes, this is phase known because everybody is alive, and the first generation had one kid, and then that one kid had a bunch of kids. Here, however, the first generation had a lot of kids right away. And typically for phase known, you want it to be in this format right here, where you have two parents who have one kid, and then that kid has a lot of kids. So because this isn't the same case here, we would actually rank this as phase unknown. So we would solve it as a phase unknown pedigree. And we know when something is phase unknown, we need to have two hypotheses. So this person, they don't have the disorder. So they would be like this, lowercase d o, lowercase d o. This person, however, is shaded in, so they do have the dominant disease. And the disease gene can be on either marker B, so you have something like this, or the disease gene can be on marker O, and you have something like this. So for the sake of this problem, either way, whichever one you pick to analyze, you should get the same answer. But let's go with this combination first, where if you have marker B, you should be shaded in because the disease gene is on marker B. So now let's rate the second generation. Here we have marker B, O. So the person has marker B and they're shaded in. So this is going to be non-recombinant. That's how it's supposed to be. Here we have the same thing, non-recombinant. Here, however, the person who has marker B is not shaded in. So recombination could have occurred where lowercase d and marker B happened, and then little d o happened. So we're going to write this as recombinant. Here we have B with the disease gene like it's supposed to be, so non-recombinant. Here we have OO. So usually if you have O, you have a lowercase d, so you don't have the disorder, but it looks like recombination occurred where now you have a big D with O, like this, and then lowercase d with O, so we're going to write this as R for recombination. Here we have lowercase do, which is what we expect. We get a lowercase do from dad and then lowercase do from mom. So non-recombinant. This is as well non-recombinant because it's the same thing. Here we have BO. We did this before and we said it was non-recombinant. OO, we did this before, non-recombinant. OO again, recombinant, non-recombinant. BO, we did this here, non-recombinant. And as well, BO, we did this here, non-recombinant. So now let's see what the third generation is going to be. They are BO, BO. They got the disease gene from mom, and then their O gene from dad. So they are non-recombinant because no crossover occurred. Here, however, when we know normally, if you have, I'll write this over here, if you have the B marker, you should be expected to be shaded in because that's where the disease gene is found. But in this case, this person isn't. So possibly recombination occurred where this person has this set. And that's why they aren't shaded in. So they are recombinant. Now here we have an A thrown in, but that's not a problem because we can go back to these parents. So I'll write this over here. So the dad is BO and the mom is AO. So the mom looks like this. And then the dad looks like this. The disease gene is going to be on B, and it isn't on O because it's not on O over here. And they have two girls who are AO, and they aren't shaded in. So it looks like they got DO from dad and then DA from mom. And that's fine. No crossover took place, so this is non-recombinant. So now that we have everything, we can begin to count and then plug into our formula. So let's see how many N's we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 N's. And then we have 1, 2, 3. 3 R's. So now let's plug into our formula where our Z is equal to the log half theta R, which is 3, 1 minus theta N, which is 15, plus 1 half theta N, which is 15, 1 minus theta R, which is 3, divided by 0.5 of the total N plus R. 15 plus 3 is 18. So now we can plug everything in to see what we're going to get. So we take the log half of theta. You always plug in 0.05 first, or whatever order you want to go in. 0.05 to the third, 1 minus 0.05 to the 15th, plus 0.5 times 0.05 to the 15th, 1 minus 0.05 to the third, divided by 0.5 raised to the 18th, and we're going to get 0.88. So after solving everything and plugging all the values of theta into our equation, we get these numbers for the LOD score. And like the previous problems, we don't have a LOD score greater than or equal to 3. So this means that our answer here is going to be no. The disease gene is not linked to the marker.